Hi, everyone. Our work is about complementing end-to-end human behavior predictors with planning approaches. Whether in autonomous driving, robot manipulation, or coordinated navigation, robots that interact with humans need to have a predictive models of human behaviors. For example, for this autonomous vehicle to decide whether to make a left turn or to slow down, it needs to anticipate what the human will do. In other words, it needs to take the current environmental information X, some historical observation H, and then map that to a probability distribution over trajectories of how human might execute. Since we cannot directly write out this mapping function F, a natural idea is to learn that from a dataset of human driving examples. And whenever we do that, we need to decide on the model class of this mapping function F. Like, how should we represent F? A very good option is to use high-capacity neural network to directly mapping from the raw input to the prediction. This is sometimes referred to as end-to-end predictors. And recently, they have been shown to be very useful, particularly in the domain of driving. And indeed, here we are showing one such example of the model at work in a very busy roundabout. So in these plots, each red dot is agent, and the model is predicting one of them. As you can see, the ground truth is in blue, and blacks are the predictions. They are spot on. However, the end-to-end predictors are not perfect. Typically, they will work as long as they have seen lots of similar examples to the new testing data that we are evaluating them on. But if there is a distribution shift, then all bets are off. Here, we are going to use the exact same model in a situation where we will use a new exit, which has never been seen during the training time. Since the model actually have the access to the route information, so if the model really learns to how to follow the route, making progress and not colliding with others, it should just work as fine. However, this is what we are seeing. So you can see that instead of predicting the agent to follow along, the model just keep on saying that agent should take a right turn. And what's funny is that where the model predicts the agent to exit is not actually an exit, but an entry. Not to mention that all those black predictions are colliding with the road dividers. And once we pass that point, somehow the model just keep on saying that agent should plow through the middle of the roundabout and then go off the road. That's why an alternative approach, which is to use planar approach to generate trajectories, which will always stay on the road, making progress and following the traffic rules. Planar is very good at that. In this case, the data is still very useful. It's just like instead of directly learning the behaviors, here we are learning to train a reward function for the planner to optimize and explain what we observe. And then there's no problem when sticking to the road, following the route, and making progress, etc. However, this also comes at a cost of naturalness. As you can see here, the planner in orange is unable to capture how wide this human is making the turn, likely because the reward function it has learned is unable to capture nuances of how humans drive. This actually brings me to the main concept that we explore in this work, since we have seen strengths and weaknesses in both approaches. So rather than having to choose one, could we somehow get the best of both worlds? So imagine this is the whole input space that we may see. And here is our training data. And we want to use end-to-end predictors on common events. But for rare events, such as stop vehicles, which we don't see often during the training time, could we just somehow detect that the end-to-end predictors will not work and then switch to the planner-based approach? And similarly, also for the out-of-distribution events, just like the totally new exit that we were showing before. But the main challenge is how? Like for any new given input, how can we tell which region it falls in? In other words, how can we detect online that we are in a situation where the end-to-end predictors will fail? The main contribution of this work is an empirical analysis of different natural approaches for this detection problem, like training an ensemble of predictors and then check on the disagreement, or we can train again to generate training-like data and then use the discriminator to detect out-of-distribution events. Or we can directly detect online when a predictor actually assigns a low probability to what we actually observe, and more. To find out what works and what doesn't, please check out our paper or come talk to us. Thank you.